So we have a question on yesterday's lecture, the homework assignments, chapter 4, section 2, question number 2. Does the function satisfy this following function f of x satisfy the hypothesis of the mean value theorem on the given interval? Give reasons for your answer. Well, what are the hypotheses for the mean value theorem? It says that a function is continuous and differentiable on all interior points inside the function. Does this satisfy the conditions? So, is it continuous everywhere? Are there any discontinuities between 0 and 7 in this interval? The square root of x, 7 minus x. It's not differentiable everywhere? It's not continuous? Where is it discontinuous? Right. Yeah, so it is continuous. Now, is it continuous at every point, including the endpoints? Or is it an open interval? Remember, the hypothesis for the mean value theorem says it has to be differentiable on what? The open or closed interval? On the open interval. Sorry, so it's continuous at every point and differentiable on all the points. So is it A, B, C, D, or neither? None of them above. So we have to ask ourselves, is it continuous? Yes or no? Yes. So C and D are no longer good options. Is it differentiable at all the points on the interior points? If it's continuous, that means does it have a slope? Does it have a rate of change in all the points? Yeah, it has to. Yeah, because that's what we learned when we talked about limits. So which one is it? Is it A or B? Very good. Because it satisfies the conditions. It has to be continuous and it has to be differentiable on the interior points.
Okay, so we don't have to like solve it out like we did yesterday with the mean value theorem.
No. All this one's asking is just satisfying the hypothesis. This is just looking, and if you remember, this is differentiable. It's continuous on the entire interval of the domain, 0 to 7. But the differentiability has to be on the open interval. That's just straight definition, straight from the definition of mean value theorem.
Okay, thank you.
Yep. You're welcome. All right. Now we're going to move on. We're going to look at, we're trying to get to a point where it'll help us to graph any type of polynomials we get. The last section, what did the first derivative tell us? What did it find for us? That's chapter 2. What did last section tell us? What did we use the first derivative to find? No, if the derivative exists, it has to be continuous. But that's not what that did yesterday. Look at your notes from yesterday. What did we talk about? We looked at the mean value theorem. What's the mean value theorem good for? It helps us define continuity, differentiability of a function. We looked at extrema points, maximum, min, global, local. We look at extrema points. So when the f prime of x is equal to 0, what does that tell us? It's a vertex. And we also talked about how do we know if it's a maximum minima? By looking at the slopes of the line. If this is our point C on our interval, look at points to the left of it. If the slope is positive to the left of it and the slope is negative to the right of it, then the only way what that defines is this one has to be a maximum. Because think about it. If you're going up the hill and then back down, you had to have reached the top of the hill before you start going down. If you're going down to the hill and you start going back up, well, there has to be a point where you're at the very bottom of the hill. And that's where this first one, this section begins. Increasing and decreasing functions. We're introducing new terms also. Monotonic. What do you think monotonic means? Mono means what? Singular, one. So if it's monotonic, it's either increasing or decreasing on an interval. So, for example, the function x squared. On the domain negative infinity to 0, what's the function always doing? Is it increasing or decreasing? It's decreasing. And from the interval 0 to positive infinity, it's always increasing. So it's monotonic on both of those sides. Which brings us with respect to the mean value theorem, corollary number 3. Suppose f of x is continuous on the closed interval AB. And differentiable on the open interval AB. Which is the basic premise of the mean value theorem. So here's the corollary. If the first derivative is positive at each point x in the open interval, then what does that mean the graph's doing? Is it increasing or decreasing? If the slope is positive. Yeah. Then f of x is increasing on the closed interval. Conversely, if f prime of x is negative, is less than 0, f prime of x is less than 0 at each point x in the open interval AB, then our function f of x is decreasing on our closed interval AB. How do we find our critical values, our critical points? Yes, we find the first derivative, then no. Pretty much our critical points are looking at where the slope changes. Take the first derivative, set it equal to 0. So example 1. Find the critical points of our function f of x equals x cubed minus 12x minus 5 and identify the open intervals where the function is increasing and decreasing. All right, so my first step is what? Find the first derivative, which is 3x squared minus 12. Which would be x squared minus 4. Now, what else can we do with this? 3x squared minus 4 can factor out into what? Yes. It's a difference of two squares, which makes it x plus 2 is minus 2. So our critical points are at -2 and 2. So x equals -2, x equals 2. What happens to the left of it? So from this interval, so from here we have -infinity to -2, -2 to 2, and 2 to +2. Those are my intervals in which I'm looking at. Before going any further, let's jump back to algebra. Our function x cubed minus 12x minus 5. Can we guess what kind of graph it's going to look like? How many x-intercepts are we going to have? At most, we'll have 3. What does the end behavior tell me? Since it's an odd degree, what do we know about the end behavior of the graph? Do they go the same direction or do they go opposite directions? Yeah, because x squared, they go the same place. X cubed, the opposite. So we know they go opposite directions. Is it increasing or decreasing? Yeah, because the leading coefficient is positive. We know from this end it's going to go up, this end it's going to go down. And we know that our y-intercept is at -5. We just don't know exactly where the x-intercepts are. Can we figure that out? Yes, using Descartes' rule of signs, if we're using uh, the uh, the zero product principle, we can figure out the x-intercepts, which we're going to have to do that for the next section out of this textbook. All right. Now we have our derivative. What do we have to do? If we pick values inside these intervals, what is that going to tell us? If we have the first derivative tells us slope. If the slope is greater than 0, is it increasing or decreasing? It's positive, so it's going up. If it's negative, it's going down. So that's what's going to help us here. Pick a value in this interval, any value. Yeah, so we'll pick x equals -3. So plug that into our equation, our first derivative. -3 plus 2, -3 minus 2. So is the answer going to be positive or negative? Since both of these will be negative, negative to negative is positive, we know our answer is going to be positive, which is greater, which tells us it's doing what on the left of that critical point. Since it's positive, it's increasing. So once we found the second derivative, choose a value in that interval. And then if it's positive, we know it's increasing on that side. Pick another one in the middle interval, 0. Plug that in the first derivative. And we get 12, or -12, which means it's decreasing. And like in the third one, in the third interval, let's pick a positive value and plug it in the first derivative. 3, 3 plus 2, 3 minus 2. So it's positive, so it's increasing. Again, it doesn't tell us anything that we didn't know already from algebra. We know our graph has to look at something like this. Again, that's what algebra tells us. We go calculus tells us now we know that our vertices occur at -2 and +2. Can we find the exact locations? How? Yeah, plug -2 and +2 into the original equation, and then that'll give you the exact values of those locations. So we know between this point and this point, it has to be going down, has to cross through -5, and it has to be going up from that side. So we knew that already. Let's see. Let's now talk about the first derivative test. For local extrema. Now, what does that going to tell us? The first derivative test for local extrema. What is that going to tell us? What is that going to show us what it looks like? Well, actually, I have those values here for you. There. That's the one we just did. We know at -2, if we plug it in there, we get 11. At +2, we plug it in there, we get -21. And it crosses through -5. Our our x-intercepts, we can calculate that using algebra. And that's what our graph's going to look like. So let's look at the first derivative tests for local extrema. Because remember, the mean value theorem tells us what? We have to be on a closed interval. So our endpoints are included. And remember when we looked at maximum minimum points yesterday, we had to look at which points, the A value, the B value, the endpoints of our interval, as well as all interior points that were critical values or critical points. Now, if the first derivative is positive, that tells us it's increasing. What does it tell us when it's 0? It's what? At 0? It's nothing. It's like a vertex. It's a horizontal line. But if we go from f prime being positive to f prime being positive, is that between there? Is that a vertex? No. It simply means that it has a leveling point and it goes on further. But then this side, we have where f your first derivative is positive, your first derivative is 0, and then your first derivative is negative. Increasing, 0, decreasing, that means this is a maximum. Conversely, if it's negative, 0, then positive, this one has to be a minimum. Now, why is the first derivative undefined at that point there? A cusp, yeah. But because you can't have corners, cusps, or oscillations or discontinuities. Because that is a point of a cusp, it's not differentiable, so it's undefined. But does the point exist? Yes, because this is an example of a continuous function. So does the absolute value, does the maximum exist at the point? Yes. So you can have an extrema where the first derivative doesn't equal 0. Remember the two conditions we talked about yesterday? Where can extrema occur? When first derivative equals what? The extrema occur when first derivative equals 0, obviously, or where it's undefined. That's why we have to look at both of those points. So when we look at maximum minimum values, you look at the endpoints and you look at everywhere the first derivative is equal to 0 or it's undefined. And then back on the other side. All right, let's look at an example here. Find the critical points or critical values or of this function. So what are my critical values or critical points? And then it goes a bit further. It says, then identifying the open intervals where f is increasing and decreasing. And then C, find the local and absolute extrema. So go ahead, find them for me. Okay, so the first thing we got to do is what? Find the derivative. We'll multiply these out. We get I distributed. It makes it much easier than using the product rule. Then I find the derivative. So the derivative of x to the 4/3 is 4/3 x to the power 1/3. 4 times 1/3 x to the power 2/3, negative 2/3. Combine those together, what do you get? You get 4 x to the power 1/3 over 3 minus 4 over 3 x to the 2/3. So how do I combine these two? What do I need? So they both have a 3. This one has an x to the 2/3. So I got to multiply this one x to the 2/3 over x to the 2/3. X to the 2/3 times x to the 1/3 is just x. So our first derivative, to see what x values we need, we have either one of those in the denominator is better. So what are our critical values? Our critical points? Where does the first derivative equal 0? at 1. A fraction is equal to 0 is at the top is equal to 0. So we set x minus 1 equals 0, it equals 1. Is that the only critical value we have? No, because we can't also, where is it undefined? At x equals 0. So these are our critical points. So our interval at 0 and 1, we have from negative infinity to 0, from 0 to 1, and from 1 to infinity. Those are my intervals I'm looking at. Pick a test value, which is any value in those domains. Negative 1, 1/2, and 2. Plug those into my first derivative. And all I'm really worried about is it going to be positive or negative? So it's my first derivative is 4x minus 1, 3, 3x squared. So when x is negative 1, will the answer be positive or negative? Well, first off, the bottom can never be negative because it's x squared. So it'll never be negative. So the only thing that'll make it negative is the top. If we plug a negative 1 in here, negative 1 minus 1 is negative 2. So this one is going to be negative. So it's decreasing. At 1/2. 1/2 minus 1 is negative 1/2. So this is also less than 0. So it's decreasing. 2 minus 1 is 2. So this one is greater than 0. So it's increasing. So we found the intervals. We found what's happening in those intervals. So we know that from to the left of 0, it's going down. At 0, it's still going down. But it's undefined. Remember, if 0 is on the bottom, then it's what's happening there. It's undefined. So it's a vertical asymptote. And then at 1, we'll see what's going there. So it's 4 over, that's 0. So that's going to be our low point here. So we have a min. Decreasing and increasing. So it's going down, then back up. So we have a minimum here. What do we know about the entire function? Looking at this entire function, let's look at this one. What do we know about the end behavior? Is there an odd or even function? It's odd because it's a cube root function. And it's positive. Yeah, but it's also fourth. That takes care of the oddness. So it's now an even function. So we know when this happens is both ends of the graph have to point in the same direction. And since its coefficient is positive, they both point up. So our graph, we know at 0, we have a vertical asymptote. So it's going to be coming down here. It's going to go down further. And then it's come back up. Whatever our intercept is, it has to be going back up. There's going to be some curves in there, of course. But we haven't gotten that far yet. So at 0, it's gonna go down. It's gonna be a vertical asymptote there. And at 1, we have our minimum point. So it's absolute min. We get 1 minus 4 at -3 when x equals 1. Because this point here is 1, -3. Example 3. Same questions. But now we're going to use this equation. Find the critical points. Find the intervals. We're increasing and decreasing. And then the local and absolute extrema.
Sir,
Yes.
I have one quick question. On the example above where you had absolute min at -3 when x is equal to 1, do you plug the 1 back into derivative or the original function?
To find the point, the original function.
Original function, okay.
Yeah. So this point is found by plugging my critical value in the original function. Yes, I'm sorry, I should have said that earlier. Good point. To find the locations of the vertices, once you find the critical points, the critical values, then you plug them back into the original equation to find the locations of the points. All right, let's go and fix this one. So the first thing we have to do here is first derivative. Unfortunately, this one's not gonna it's not gonna be fun because we can't do what we did last time. Because we have an e and an x to the power, so we have to use the product rule. So this one is x squared minus 3. G is e to the x. F prime is 2x. G prime is e to the x. So the product rule. So we have 2x e to the x plus e to the x squared minus 3. 2x e to the x plus x squared e to the x minus 3 e to the x. Actually, since they all have e to the x, we get 2x plus x squared minus 3 e to the x squared plus 2x minus 3. So second sign of minus, they have opposite signs. What times what is 3? When you subtract them, you get 2. The bigger number gets a plus. 3 and 1. So how many critical points do I have? 3 or 2? ¿Por qué? Because if we multiplied these, it'd be x squared, and there's another x there. This is a thinking question. How many critical points are we going to have? Well, that x will find us the critical points. How do we find the critical points? And do what? Right. Now we take each of these set equals 0. Can e to the x ever equal 0? No. So because it's a increasing function, it's always above the x-axis. So this one does not x-intercept. So we only have two values, -3 and 1. Right. So our intervals are going to be at -3 and 1. Those are my critical values. So from -infinity to -3, -3 to 1, 1 to infinity.
For critical points, are they just by setting equal to 0, or will we have to find the undefined values as well?
Or it's undefined also.
Okay.
But since that was a quadratic equation, this one never equals 0, and these two are easy. So, but you're right. If we had had a fraction of 1 over x, then we'd also have to use 0 because, or anywhere it's undefined.
Okay.
So my test value will be x equals -4, x equals 0, and x equals 2. Because all I really care about is it positive or negative. And because our derivative factors out so beautifully, it's easy to see whether it's increasing or decreasing. So at -4, we got e to the -4, -4 plus 3, -4 minus 1. That's -1, -5. So it's e to the -4 times 5. So it's positive. Because e to the x is always increasing at a positive number. So it's increasing at this point. At 0, we have e to the 0 is 1, +3, -1, so it's -1, so it's less than 0, so it's decreasing. So what do we know about the critical value of -3? Is it a minimum or maximum? It's a max. Only thing we know, it's a local maximum right now. We don't know if it's an absolute max until we get the rest of them. Do we have endpoints to check also? No, because the function never defined a domain. So there is no endpoint. So it's going down here. What happens at f of 2? E to the 2, 2 plus 3, 2 minus 1. That's going to be positive, so it's increasing. So we have a local min at 1. What were the three things we're looking for? Increasing, the intervals of increasing. So it's increasing from negative infinity to 3 or negative 3. It's decreasing from negative 3 to 1, increasing from 1 to infinity. So at negative 3 and at 1. Do we have a y-intercept? How do we find our y-intercept? Yeah, so x is 0, so that's 1. 0 minus 3 is negative 3, so the x-intercept, the y-intercept is at negative 3. Do we have any x-intercepts? Actually, let's see. We know so we know the values. So we have it's increasing here, decreasing, and increasing. So at negative 3, we haven't don't know about the x-intercepts. X-intercepts we know are going to be where? So y equals 0. It's going to be plus or minus radical 3. Radical 3 is less than 2. It's about there. Yeah. So it's got to be increasing there. There's my x-intercept. So my vertex is there. But at negative 3, we have a vertex. So something has to happen like this. Because we have at negative 3, we have to have a maximum, a local maximum, which means that only reason it's a maximum because on the left side is increasing, on the right hand side has to go down. On that 1, we know we have to have a minimum because it's going down, cross through negative 3, and then back up. So, and it doesn't have any more x-intercepts, so it has a horizontal asymptote. So that's what our graph looks like. So you see how you put all this information together? Once we knew that we have to have a vertex here and here, on the left side, it's increasing, but there's no x-intercept. The only way that could be true is if it's like this, like an exponential function. Then we have an x-intercept, so it has to go down to this vertex, crossing through negative 3, and then back up. So it looks something like that. All right, that does it for that one.